This lecture is part of an online course on algebraic topology and will be about the fundamental group. So the fundamental group is also called the Poincare group, or the first homotopy group of a space, and is denoted by pi1 of x, and x0 is going to be some sort of base point in the space. The subscript 1 is because this is the first homotopy group, and there's also an nth homotopy group for high numbers of n that we might talk about a bit later. So I'll just recall what this is. This is just the loops in x that start from the point x0 and go and end up in x0. So a typical element of the first homotopy group might be like that, except these loops are in x up to homotopy. So you remember, roughly speaking, this means two loops are considered the same if you can slide one to the other. So more precisely, a loop is going to be a continuous map from the interval 0, 1 to x, which takes 0 and 1 to the point x0. And we recall a homotopy between loops f and g. So suppose I've got loops f and g, then a homotopy from f to g will be a map from 0, 1 times 0, 1 to x. So if this is considered to be t, then at t equals 0, the map from here should be f, and at t equals 1, the map should be g, and at all times the beginning points and end points of this interval should always be x0. So we want to show that this forms a group. So composition is fairly obvious. So if we've got a loop, a red loop and a blue loop, then we can compose these and get a new loop that first goes around the red loop and then around the blue loop. So the way this is done is, if you've got an interval 0 to 1, then if you first do the red loop, from 0 to a half you're going to go along the red loop, and from a half to 1 you're going to go along the blue loop. Now we should check this is associative. And at first sight this looks kind of obvious, because if you do a red loop and then a blue loop and then a green loop, it obviously doesn't matter whether you do the red and green first and then the red and blue first and then the green, or do the red first and then blue followed by green. Or if you look more carefully, the loops aren't quite the same, because the loops are actually given by maps from the unit interval into the space. So if you do the red loop and multiply it by the blue loop first and then multiply it by the green loop, what you get is from 0 to a quarter you're going along the red loop, and from a quarter to a half you're going along the blue loop, and from a half to 1 you're going along the green loop. On the other hand, if you multiply the blue loop and the green loop together first, it sort of looks like this. You go along the red loop from 0 to a half, and then along the blue loop from a half to 3/4, and then along the green loop from 3/4 to 1. So these compositions aren't quite the same as maps from the unit interval to the space x. However, these maps are homotopic, because you can obviously just sort of reparameterize things by sort of squashing down this green bit and expanding the red bit. So although the loops aren't associative considered as maps from 0, 1 to x, they are associative up to homotopy. We should also check inverses. And again, it's obvious what the inverse of a loop is, that if you've got a red loop going from x0 to itself, going in one direction, then its inverse should obviously just be the map going in the other direction. And again, we have a slight problem that the composition of the red loop and the blue loop is not actually the trivial loop that's always at x0. However, it's homotopic to this. And you can see this because instead of going all the way along the red loop and then back along the blue loop, you can sort of go 3/4 of the way along the red loop and then back along the blue loop. Or you can go halfway along the red loop and then back along the blue loop and so on. So you can sort of slide the red loop followed by the blue loop down to a map that just stays at the point x0. So the homotopic group pi1 of x with base point x0 is actually a group. And that's because you're only taking loops up to homotopy. If you didn't take them up to homotopy, it wouldn't be a group. Now let's calculate it for some spaces. First, let's take x equal r to the n, and x0, doesn't matter what x0 is, it could be the point 0. And then pi1 of r to the n is just the 0 group. And that's because any loop is homotopic to the trivial loop. By the trivial loop, I mean the loop that just stays at the point 0 everywhere. And the reason for this is that Rn can be squished to a point. So what do I mean by this? Well, informally, it means if you take Rn, say we take R2, then you can take any point and you can gradually move it to the origin. So this is at time 0, and at time 1/2 you get there, and at time 1 you get there. And similarly, if you take any other point here, at time 0 you might be there, and at time 1/2 there, and at time 1 there. So you can sort of squish it all down to the origin. Well, saying something can be squished is not actually a precise mathematical term, so I'd better explain what this means. What this means is the identity map from Rn to Rn that just takes every point to itself is homotopic to the map taking Rn to 0 in Rn. And here the squishing down to 0 is just the homotopy taking the identity map to this. And using this, you can see that any two maps from any space x to Rn are homotopic. Because you can any map from x to r to the n is just homotopic to the map taking x to a point, because you can just sort of use this this map to squish it down to a point. In particular, pi1 of Rn with base point 0 is just trivial because any two of these maps are homotopic. Similarly, you can see that any convex set x in r to the n has pi1 of x with respect to any base point equal to 0, because if a set is convex, you can again sort of squish it down to any point. And you could do the same for any star-shaped region if you like. The fact that Rn can be squished to a point is another way of saying that Rn is contractible. So this just means the identity map is homotopic to a constant map. And contractible spaces in algebraic topology are in some sense the trivial spaces. All their homotopy and homology and generalized homology groups always vanish. There's actually an interpretation of this in terms of category theory. If you take a category whose objects are topological spaces and whose morphisms are continuous maps up to homotopy. In other words, you consider two continuous maps to be really the same if they're homotopic, then contractible sets are just the sets that are isomorphic to a point in this funny category of topological spaces and homotopy classes of continuous maps. So so a homotopy theorist thinks that you know, an n-dimensional vector space is indistinguishable from a point. So let's find a fundamental group of something that isn't trivial. So now let's find the fundamental group of a circle with respect to some sort of base point. And here, as we mentioned in the first lecture, if we've got a continuous map from the circle to itself, it's got a winding number. The circle can go round itself n times. And not very surprisingly, this means that the fundamental group is just going to be the integers because it's determined by the number of times you wind round S0. So how do we do this? Well, we're going to write S1 as being the real numbers modulo the integers. You identify two real numbers if they differ by an integer. So we get a map from the real line onto S1, and you can think of this as being a sort of helix covering S1. So here we've got S1, and here we've got a sort of copy of R, which is winding round and round it like this. And now we're trying to look for maps from S1 to S1, taking the base point to whatever the base point here is. And what you notice is that we can think of this map S1 as being a map from I1, the unit interval, to S1, taking 0 and 1 to S0. And what we can do is we can take this map from I1 to S1 and we can lift it to a map to the real numbers. So here this is going to take 0 to 0, where we have the sort of base point 0 in R. And the reason we can lift this is that this map from R to S1 is a sort of local homeomorphism. Each point of S1 has a little neighbourhood such that it's isomorphic to a little neighbourhood of its inverse. And this means that if we've got a map from I1 into S1, we can sort of lift it locally to R, and because I1 is compact, we can glue this together and kind of lift it globally, so that I1 is connected or something. So in other words, if we've got any map from I1 to S1, it might sort of go backwards and forwards a bit. We can lift it up here. It might go backwards and forwards a bit. And it might not end up at 0. It might end up at some other point mapping to 0. So any map from 0 to 1 to S1, taking 0 to the base point 0, lifts to a map from 0, 1 to R. And again, it takes 0 to 0, and it takes 1 to some integer n in Z. And now this integer n is going to determine its homotopy class. And you can see this just by sort of drawing graphs. So here I've got a unit interval from 0 to 1, and I've got two maps mapping it to the reals, and one map might look like this, and the other map might look like this. And it's kind of obvious these two maps are homotopic because you can just slide one down into the other if you like. So two maps from S1 to S1 mapping the base point to the base point are homotopic if and only if the lift to R1, the lifts to R1 have the same image of 1, which will have to be an element of Z. So this shows that pi1 of S1 is just isomorphic to the integers, and the isomorphism is just given by the winding number, the number of times you go round S1. So that's done the fundamental group of a one-dimensional sphere. Now let's take a look at a two-dimensional sphere. So what's pi1 of S2? Well, suppose the map from S1 to S2 is not on 2. then its image is a subset of S2 minus a point, and S2 minus a point is just isomorphic to R2, which we saw was contractible. So if this map is not onto, then it's homotopic to a constant map. And at first sight, this seems to say the fundamental group of S2 is trivial, because S1 is one-dimensional, so its image can't be a two-dimensional set. Well, actually, its image can be a two-dimensional set. We have a slight technical problem caused by space-filling curves. That the image of a one-dimensional curve can be two-dimensional. So these were originally examples of these were originally given by Piano and Hilbert and so on, and they were rather upsetting to people when they were first discovered. I'll just very quickly give a simple example of one. We might take just take a right-angled triangle, and I'm going to approximate this curve in several steps. So the first approximation is going to be that the curve goes along like that from 0 to 1. And then I'm going to, instead of making it go like that, I'm going to make it go like that. So here's the image of 0, and here's the image of a half, and here's the image of 1. And then I'm going to divide this triangle in two. And now I'm going to make the curve go along here, up here, down here, and along here. So this is the image of a quarter and 3/4. You notice a quarter and 3/4 of the same image. Then I'm going to divide the triangles in two again, and instead of going along here, I'm going to go along here, so the image of an 1/8 and 3/8 is here, and the image of 5/8 and 7/8 is going to be there. So I should use different colours so you can see what the curve is doing. So the curve is coming down here, down here, down here, along here, along here, along here, along here, and along here. And then the next iteration, I make the curve go like this, up here, down here, along here, and so on. And with a little bit of effort, you can see this does actually give the limit of these is actually a well-defined function from the unit interval, and its image is the whole triangle. So we've got the image of the interval is actually a two-dimensional triangle. So the image of S1 maps to S2 can be onto. Well, this isn't very difficult because we can just sort of shift it a little bit so that it's not onto. So we can cover S2 by, say, 4 disks, and each of these disks should be isomorphic to R2. And then we've got to map I from the unit interval to S2, and because I1 is contractible, we can arrange that there are a finite number of points, 0 less than A1 less than A2 less than AN less than 1, such that the image of each of these intervals from AI to AI plus 1 is contained in one of these disks. And then because it's in a disk, we can then straighten it. Well, we can't quite straighten it because S2 is actually a sphere. So when I say straighten it, I mean we can replace this map by a homotopic geodesic from AI to A plus 1. So the map from I1 to S2 is homotopic to a curve which has a finite number of geodesic segments, and if we've got a finite number of geodesic segments, this is obviously not onto. So in other words, if we've got a map from S1 to S2, if it's onto, we can first of all make it homotopic to something that isn't onto S2, and then we can contract it down to a point. So pi1 of S2 with respect to a base point is just trivial, and the same argument obviously applies to 3-dimensional spheres and 4-dimensional spheres and so on. So let's give a few applications of this. So the first application, let's just show that two-dimensional space is not isomorphic to three-dimensional space. I mean, it's kind of completely obvious that two-dimensional space is not homeomorphic to three-dimensional space, but it's maybe obvious, but it's not actually all that easy to prove if you try and do it from scratch. And one way of doing it, well, you might try working out, say, pi1 of both sides. Well, that's going to fail because pi1 of both of these is just trivial. In fact, these are both contractible. So you might think algebraic topology can't actually distinguish them because algebraic topology says all contractible spaces are really the same. But what we can do is we can remove a point from these. So it's enough to show that R2 minus a point is not homeomorphic to R3 minus a point. And now we can work out pi1 of both sides. So pi1 of R2 minus a point with respect to some base point is just z, and pi1 of R3 minus a point with respect to some base point is 0. And why is this? Well, the reason is that R2 minus a point can be squished down to a circle. And to see this, let's take R2 minus a point. So we're going to remove this point. And here's a circle S1. And what you notice is that we can take any point and we can gradually move it to some point on the circle like this. So what we're doing is we're starting at time 0, and at time 1/2 we sort of go halfway to the circle, and at time 1 we move the point to the circle. As usual, the term squishing is not really used mathematically. Mathematicians don't say squish, they say deformation retract. Because if you're applying for a grant and you say you want to squish things, your grant is going to be rejected. But if you say you are studying deformation retracts, everybody will be much more impressed and give you lots of money. So what's a deformation retract? Well, if you've got a space A contained in a space X, a deformation retract means you sort of take the identity map from X and kind of gradually deform it until it's mapping A to X. So what we do is we have a family of maps ft from X to X, which have to be continuous. So f0 is going to be the identity. So f0 of X is just equal to X, and f1 of X has to be in the subspace A, and ft of A must be equal to A for all A in the subspace A. So what's happening is this is just squishing down the space X into the space A. I should say this is sometimes called a strong deformation retract because this condition here isn't always assumed, but I'm going to take this condition here. And you can also check that if a space is a deformation retract of another space, then it's got the same fundamental group, because again you can just sort of squish all homotopies between things down into the subspace. So this is the same fundamental group as S1, which is Z, and similarly we can squish this down into S2, so this gets squished into S1 and this gets squished into S2, which we saw had 0 fundamental groups. So these two spaces are not homeomorphic, and therefore R2 is not homeomorphic to R3. As another application, we can say S1 is not a retract of the ball B2. In other words, if you've got S1 and you've got the two-dimensional ball B2, so here's B2 and here's S1, then there's no continuous map from B2 to S1 that's the identity on S1. So we're asking, is there a map from B2 to S1 such that F is the identity on S1. Notice that this is a retract, not a deformation retract. So a deformation retract would be sort of deforming the identity map to a retract, which is not what we're doing. Well, suppose we had a retract. Well, we've got an obvious map from S1 to B2, which is just the injection. And if we had a retract from B2 to S1, then we would have a map like this, which is the identity. And now we look at what pi1 does. So we've got a map from pi1 of S1 to pi1 of B2 to pi1 of S1. And what I didn't mention is that the fundamental group is actually a functor. If you've got a map between spaces preserving the base points, I forgot to write in the base points here, which is I should have done. If we've got a map between these preserving the base points, then we get a map between fundamental groups. And I'm getting bored of writing out the base points, so I've just missed them out here. And now this group is equal to 0, and this group is Z, and this group is Z. On the other hand, the composition of these two must be the identity. And there's you can't have the identity map from Z to Z factoring through the 0 group. So S1 is not a retract of B2. In other words, if you've got a membrane with boundary a circle, there's no way to sort of map the membrane to the circle. Again, this is sort of intuitively obvious, but it's a little bit tricky to actually prove rigorously. As a final application, I'll prove the Brouwer. I can't remember how to spell Brouwer. Fixed point theorem. So the idea is that if we've got any map B from a two-dimensional disk to a two-dimensional disk, then F has a fixed point. In other words, if I take this piece of paper and crumple it up and put it down so that it's above where it used to be, then there's at least one point of the paper that's above where it used to be. And for this, suppose we've got a map from B2 to B2. Suppose it has no fixed point. Well, if I take B2 here, so I've got a map from B2 to B2. So if I've got any point x, then f of x is not equal to x. So there's some direction from x to f of x. So we get a map from B2 to S1, where this map gives us the direction from x to f of x. Well, we haven't finished yet. What we need to notice is that we now get a map from S1 to B2 to S1, and this looks a bit like the one before, except in the previous example where I wanted to prove there wasn't a retract, this map from S1 to S1 was the identity. However, it's not the identity here because if I take a point here and I map it to some other point, then this direction isn't the same as the corresponding point S1. In fact, what's happening is that if I've got any point of S1, then this map must map it to something in the opposite semicircle. Well, this is enough to show this map from S1 to S1 has winding number 1. Because as you go once around S1 clockwise, the image of these points must also go once around S1 clockwise because you're always in the opposite semicircle from your point. So again, this implies the map from pi1 of S1 to pi1 of S1 is the identity. However, it factors through a group whose pi1 is 0, so this is not possible. So this proves the Brouwer fixed point theorem for two-dimensional spaces. Okay, so next lecture I'm going to be giving some more calculations and applications of the fundamental group.